Good afternoon, everyone. Thank you for joining. I am Sanket and I work with LinkedIn as an SRE. I work on a capacity engineering team at LinkedIn. 3 years back, I was new to the industry, started as an intern, and the project that I was assigned to was about HBase. HBase is a database that works on a distributed file system called HDFS. Now, I was an intern. I had no idea what any of these things meant. I had no clue what any of these things are. And my mentor suggested like the best way to learn something is to by doing it. So let's us also get started. Uh, Here's what we're going to talk about. So we'll first be exploring typical file systems. Typical file systems means the ones that we use day to day on our cell phones, on our laptops, desktops. We'll see how are they built up, what are the concepts that goes in. We'll see how does the writes go. If you want to read a file, what exactly things does go in, what are the things involved, and how do you ultimately get your content of the file. We'll also see if you write to a file or create a new file, how will that flow look like? What are the challenges? We then will take the normal typical file systems and we'll try to evolve it into a distributed one. We'll try to compare both the architectures and we'll try to make sense of it. Having understood typical file systems, we'll see what does distributed look like. We'll again see if you want to read a file in the distributed environment, how would it look like? Again, the writes. And as I said, the best way to learn anything is by doing it. So I'll introduce you to a tiny, cute little distributed file system that will see how does the read and writes will look like in that one. So things will make more sense if you actually see it happening. Here's what we are not going to explore. We won't be exploring any particular file system, let's say ext4, ext3, HDFS, or any particular file system, but the architectures that we'll be seeing will be generic enough to be comparable with most file systems that exist today. So I hope that wouldn't be a problem. Conceptually, most should be relatable. And of course, answer to the ultimate question, we all know the answer to, right? So let's get started. What are file systems? To tell it in a single sentence, oversimplified way, it's a structure defined over raw storage space. What is raw storage space? Your storage devices, hard drive, pen drive, your memory cards. So we define some structure over it so that we can utilize it better. If you want to classify it on a really high level, it is made of data and metadata. We'll see how does it look like. But before we see what do they look like, let's try to build our own file system. You have a device and you have an API. What that API can do for you is you can give it an address on the disk and you can read back the content from the address. So this is what you have, a storage device, and you can read content from any random place. Now let's try to build our own file system before we explore what existing ones look like. Really basic version, we divide storage space into fixed blocks, in this case 100K. So how do you use this up? You want to put file, you put it at every 1000K offset, 100K. So you want to access the first file, you access it at 0 offset. You want to access third file, you go to 200K and access that file. Really basic, but works. There are some limitations. First being, you cannot put a file that is more than 100K. Yes. Second being, you might end up wasting some space if the file is smaller, but good for first writers, I guess. If you want to make it a bit better, resource utilization, instead of going fixed blocks, what we can do is, let's not go fixed blocks. We first, at the start of every block, we put the file size first, say 11K, and then you put the file. When it ends, you put the next file size, and then you put the content. Gets a bit better than the first approach. Say you are now having variable size files. You can have files of varying lengths, and you are also not wasting space. So works better than the previous one. If you want to make it a bit better more, along with the size, what you can do is put maybe file name. So along with the size, you can call it file1.txt, foo file, whatever. Name can be put in. And if you want more metadata around it, you can also put who owns this file. when was it last accessed, when was it created, things like that. So if you see where we are going with this metadata approach, it might sound familiar to you, an inode. So this is the kind of metadata that an inode will contain. If you don't know what an inode is, here's what it looks like. So what inode is, it is basically a structure or some sort of metadata that the file will have. So some of the things that generally will go in is who owns this file or a directory or whatever it points to, who is the group that the user belongs to or the file belongs to. The important one being type, that what kind of data the inode is pointing to, say file, directory, link, device, some timestamps, and of course in the end sizes, that how big, and the most important will be disk addresses, that is where does the actual data is located at. So do you think these are the metadata, say for a file, do you think anything obvious is missing? Maybe file name, like we have all the things but not the file name. Do you think it is missing? It is not. So we don't put file name in here. We'll see where does it go. Let's take a look. If you got an inode for a file, what will it look like? So all things will go in as usual, owner, groups, some timestamps. The type here will be differentiating, that will be a regular file. The size will be there, disk address, and if you want to read the content of the file, you'll go to disk and you will access the block number 99, and whatever the block has contains, that is your file's content. So this is what it look like for a file, like really simple, nothing fancy go in here. What will it look like for a directory? Now in Linux we say everything is a file, so a directory is also a file. Everything is a file, so directory is also a file. So it should be something similar to what an inode for a file is, right? Let's take a look. If it is for a directory, of course the type will be different. That is a directory, along with the timestamps and disk address. Only the data will be having a specific structure. So what is a directory? Directory is directory will contain other files in directory, so it's basically a list sort of thing. So how would you arrange that? So let's simplify it a bit and put it in tabular format. We'll have two columns. The first being the inode numbers, that what are the contents of the directory and inodes for that, and what do you call it. So here is the place where your name will be going. So say if a directory has inode 85 and you want to call that file or directory, whatever it is, password, so here is the place where you will be putting the name. Now this is what it will be looking like for a file and a directory. Now having understood this, let's also try to understand something that we use every day, that is links. You may have heard of it, soft links, hard links. Let's see how does it actually look like and how does it work. So we have a file here called password and inode number is 85. Now in the same directory you want to create a link. You want to create a new file called users, and it should be pointing same content as password. Really simple. Because it's a table, we add one more entry, inode being 85, and in the name column you put users. So in the directory listing you got two files, one is called password, one is called users, and because they have same inode number, they point to same content. Because you know where does the data is stored at? It's stored in inode. So both the files points to same disk blocks, and there you go, you have a link. So this is a hard link. Now how will a soft link look like? Well, in case of soft link, you won't be putting it in a directory entry. Instead, instead of the disk address, you'll be putting whatever the link it is pointing to. So that is why in case of soft link, you can put anything instead of disk address. Your file can be pointing to any random. It's just a string. You can put anything, and it may not have to be existing. While in case of a hard link, this inode number will be existing, and file system will ensure that hard link can never be broken. So that is soft link and hard link. Now, systemd is a directory. Let's take one more example. It's a directory, and you want to create a hard link for directory. So if you are following the structure and the way the things look like, what you can do is you create one more entry in the directory listing. It's just a table. Entry inode number will be 89, and you want to call it systemd hyphen link. Logically you can put it, right? Like there's nothing stopping you. It makes sense. You're just making one more entry. But why not? Like systems won't allow you to. Why not? Let's take a look. Why is hard linking not allowed for folders? Say you got this example structure. You have temp directory. Inside temp you got A. A is a directory, and inside A you create a directory called B. So temp A, B, all are directories. Now let's try to create a hard link called L in folder B. L will be pointing to A. This is just an example. So can be created if it was allowed. Now what's the problem here? Say you wrote a script that recursively lists out all the contents of the directory. So your script starts, it lists out content of temp. What it sees A. It lists out content of A, it sees B. It lists out content of B, it sees L. Now L is linked to folder A. So it lists, if it lists content for L, it will be seeing B again. In B, it will see L. In L, it will see B. So you see there's a loop here. So your script can go in infinite loop, and logically this thing doesn't make sense. So that is why hard links are not allowed. Now this was inode, this was data blocks. We are talking about file systems. So where does it fit into your raw storage space? Where does it fit in? So this is the overall simplified structure. The rectangle being the whole your storage device. We'll be partitioning it because that's what we said. What is a file system? That is a structure defined over raw storage space. So this is the kind of structure that we define, or the normal file system would define. Data blocks that will actually be containing data. We'll have an inode table where the inodes that we just saw will be going in. We'll also be maintaining two more lists called free block list and free inode list, because every time if you want to create a new file, or if you want to extend a file, you need free inodes or the free data blocks. So here's a handy list that you will be maintaining so that you can quickly grab some free data blocks or the inode. There will be a super block. Super block is metadata about your whole file system. That is how many inodes are there, how many blocks are there, what is the utilization, things like that. What is the block size? And there will be a boot block. So if in case your disk or the file system is bootable, then the booting instruction would go there. So this is the overall picture where your things would go in. Now let's take an example. You got a file system that has data block size worth of 1,000,000 bytes. You have divided into 1,000 bytes block. So you have 1,000 blocks. Now how many files you can create? You want to create 1,000,000 files that is 1 byte long. 1,000,000 files that has 1 character. Can you create 1,000,000 files? You got space for that. You got 1,000,000 bytes. Can you create 1,000,000 files? No, you cannot. Why? Because if we go back and look at the inode, you see in inode you specify a block's address. So each file at least will be using 1 block. So in this case, each file will at least be using 1,000 bytes. Whether it contains 1 byte, 5 byte, 10 bytes, doesn't matter. 1,000 block will be allocated to 1 file. So how many files you can create? 1,000. But can you? Can you create 1,000 files? Well, the answer is depends. Depends on what? Inode table. So you see, even if you have 1,000 blocks, you may not have, this is a fixed size structure as we said in the beginning. This is a structure defined over raw storage space. So the inode table is a fixed structure. So it may not have space for 1,000 inodes. So it really depends that if you have less than 1,000 inodes, you cannot create 1,000 files. Now, this was the overall picture. Now we promise that we'll be seeing how will the read look like and writes will look like. So let's take an example. Let's try to read a file that we all know, /etc/password. We all know this file. What you want in the end is whatever the content it contains. What we know about is the overall structure and inodes and data blocks. We all know what goes in. Now, /etc/password. What is slash? It's a directory. It will have some contents in it. So if it is a directory, there has to be an inode to that because all files in directory have inode numbers. So inode for directory slash is 2 because you need some place to start. You want to list out content for directory slash. You need some place to start. So inode 2 is the place you start. Now, why inode 2? because inode 0 basically means null value for inode. Inode number 1 is reserved for uh, listing for the corrupt blocks, like you maintain the list of corrupted disk blocks. So next logical choice that was available was inode 2. This is more sort of a convention, like it's not a fixed thing. So this is the convention that the moved file system will use. So there you go, you have place to start. You know slash for inode for directory slash is 2. So what will you do? You'll go back to the inode table, you'll fetch the inode 2. Inode 2, you'll find that data block associated is, for in this case, for example, 98. So you'll go to the data block section of your file system, you'll fetch the block number 98, and you'll list out the things. Now what you're looking for, slash etc slash password. So you will, in the directory listing in the table, you'll be looking out an entry for etc. Now for etc, the inode number happens to be 23. So again, you'll go back to the inode table, you'll fetch the inode 23. The inode 23, it is for directory etc. So if you list out the contents, it should be contents for directory etc. What you're looking for? You're looking for password, the next component in the path. For the password, you'll be seeing that inode is 45. You go back to the inode table, you fetch the inode 45, you see what data blocks is associated. In this case, it was 155. And finally, when you go to the data block section, you fetch the data block 155, and there you go, you have your file's content. So this is how a read would look like. Now let's talk about writes. So you want to write to a file. So obviously to write, you will be writing it to some data block. And as we just saw, to get the data block, you need the inode number for the file. So you will be doing same thing. You will be converting the name, file name to the inode, like we did with the reads case. So you convert, you get the inode number. If in case the file was a new file, that non-existing file, so you know where to go to. You have to create a new file, so you'll need a new inode, you need new data blocks. You know where to find them, right? So if the file is not existing, you will allocate a new inode from a free list. If file was existing, you need to get the data block. So from given offset, say you want to append to a file, you'll get the last data block. If you want to add something in the beginning of the file, you get the first block. You load that block into memory, because the block in the disk, you load it into your memory. If you want to append to some file, if the block doesn't exist, like you're extending file, you have to allocate a new block. So in that case, you'll allocate a new block. And finally, when you have the block in the memory, you do whatever you want, you change, append, whatever you want to do. And finally, put it back to the disk. So you do write call, and you assume that your block has been written to the disk. But is it really? Not really. When you write anything to a file, it is not immediately written it to the disk, the actual storage device. What your OS does is, even if you write it, it will kind of hold it for a while in memory, so that when bunch of enough writes has been done on the disk, it will batch all these things together and later put it to the disk in a flush, so that it can optimize things a bit. So this is the reason why in older days you've been seeing these warnings that you should not just pull out a USB device, or you should safely remove the device. This is the reason why, because you may have written things, your OS might not have flushed those blocks into your actual storage device. So this is why your OS advise you to do safety remove, so that it can do all the pending writes to your disk. And this was the reason why you've been seeing those warnings. Now, if you look at the write process, you see it's a multi-step process, right? Things can go wrong when you are doing this. Power cut, OS crash, things like that, it may happen. And if you were to get stuck somewhere in between, that you were on step 2 or somewhere in between, and these things happen, then your file system may go in inconsistent state. You're going to do something, but you didn't finish it, so your file system is not consistent anymore. So to overcome these problems, new version of file system introduced the concept of journaling. What is journaling? Basically, the structure we saw, there's one more section for journaling. So in journaling, what you do is you write what you're gonna do. You are gonna do these 3 steps. You first write that I'm gonna do these 3 steps, and then you go and actually do it. So you've written what you're gonna do, and while actually performing these 3 steps or whatever steps you're doing, if something goes wrong and if you come back up, then you actually know that what operation were going to be executed, and if you know those operations, you can roll back and come back to the consistent state. So that's what journaling is. You write what you're going to do and then do it, so that in case something go wrong, you can recover. Now there are some problems with this. So first being, you are writing contents to a disk. A disk is a device. Device can go wrong, go bad, and it's a single point of failure, right? If it is gone, your data is gone. If say Thanos snaps his finger, half the storage devices of the world are supposed to disappear. What happens in that case? 50% chances that your data will be gone. Single point failure. Other being, it's a physical device, so it can only read n number of reads bytes, or it can only write n number of bytes per second. So if you have tons of CPU power and you want to do tons of processing from this data that is relying on the disk will be a bottleneck issue because it has limits. And third being, it's a storage device, and it's been manufactured in has storage capacity that is fixed. So tomorrow, if you want more space, you cannot expand this because it's a piece of hardware. So these are some problems with it. Some of these can be overcome by using RAID, that is redundant array of disks. So still some problems associated, like it is presented as a single volume to your OS. So if your server or the host crashes, your single point of failure sort of problems still persist. So we won't be going into RAID configurations, and we'll take a look at next logical step that will overcome some of these problems, called distributed file systems. Now, what is it? A file system but distributed. Now, you may ask, distributed, but distributed across what? Across disks, across hosts, across data center, across geographies. In this case, it will be distributed across network of hosts. We'll see how does it look like. But why go distributed? Of course, we want to avoid single point of failure. So if a host or a disk goes down, your file system, your data should be still available. You should still be able to access it. You want to avoid bottleneck problems. And of course, you also want to scale your storage space. You don't know, because data size is ever increasing, so you don't want to be bound by your storage space. Now let's take a moment, look back what our file system looked like. It was made of metadata and data, to classify it on really high level. So all the inode table, free inode list, superblock, all this was metadata and the data part. Now let's try to make it distributed. So let's take metadata, put it on one host. Let's take data, put it on several hosts. There you go, your file system is distributed. Now you may not sound convinced, but let's try to see the file that we saw it in our normal file system example, /etc/password. Let's see how does it look like in our distributed file system. So host 0 is metadata host. What kind of metadata file will have? File will be divided into blocks, and blocks will be placed somewhere. So in our earlier case, there was only one copy of the block in data blocks list. Now because you're making distributed, you want to tolerate failures, you will be creating multiple copies. So say etc password was divided into 2 blocks, block 0 and block 1. And here we have chosen to create 2 copies. So block 0 is placed on host 1 and 2, and block 1 is placed on host 2 and 3. Of course, this is configurable, but we've created 2 copies for now. Now, this is what it will look like in our distributed environment. Now, let's see how does it solve our problems. So, the first problem we talked about was a single point failure. How is it solved? Because we have 2 copies or multiple copies, say host 1 went down, block 0, first copy of block 0 is not available, but it's still there on host 2. So, this is how that part is solved, single point of failure. Now, you may ask that there's only one copy of metadata. So what if this thing goes down? You're out in the water, right? We'll see how different file system handles this single point of failure of metadata part. But at least for data part, you're sorted. There is no single point of failure anymore. You got multiple copies. The other problem was bottleneck issues. Uh, Now you got two copies. So if somebody wanted to read etc password file, they got multiple options to go to. So this really helps. Say, let's take an example. We had a data set of LinkedIn's member data. So it will be a sort of a table, and tons of queries, business intelligence queries will be needing access to this data set to join some other tables. So these are, as you can foresee, these are really demanding data set, LinkedIn's member data set. So what you can do in that case is, for that file, you can increase the replication factor. Instead of creating 2 copies, you create 10 copies, for example. So each blocks or of the file will be available on 10 different hosts. Now 10 different hosts will have their own independent bandwidths. So now instead of in case of normal file system, you got 10 times more bandwidth in this case. So if users are running queries that are distributed across 10 hosts, and you got 10 times more bandwidth. So there you go, you solve your bottleneck problems. And the last problem that we discussed was storage space, that storage is not scalable. So in this case, you can always go on and add one more host, say host 4, host 5, and your storage space will scale. Now let's try to read same file. You got someone who wants to read. Metadata is located on metadata host. So here's what you will do. First, client will go to metadata host. It will tell that I want to read this file. What metadata host will tell is these are the blocks and this is where they are located. So now what client will do is it will go directly to the host that contains those blocks and it can try to read. So you can see that it is only connected, the metadata node is contacted only once, and now the client can go directly to the host that contains the blocks, actual blocks, and go read the blocks. If it wants to read block 1, it can go host 2. Now in case host 1 was down, if it's down for some reason, your client knows that where else to find block 0. So if host 1 is down, it can go to host 2. Similarly for block 1. Now you can see a potential bottleneck here, because to read or write every file, you need to go to metadata host. So this can be a potential bottleneck, but in most cases all this metadata is kept in memory, so it doesn't take much of computation power for master. And at a very later point of time, when it starts to become a bottleneck issue, there are some ways to shard it. So you can have 2 metadata nodes, and they distribute the metadata amongst them. Now, what if you want to write a file? Well, somewhat similar. You'll first go to metadata node. You'll tell that, hey, I want to write this file. What metadata node will do for you is it will divide you into blocks, and it will also tell you that this is where the blocks are supposed to go. So it will do the allocation part basically, and tell client the allocation. Now client will go and directly write those blocks to the data hosts. Now while writing, just to optimize things a bit, what you can also do is you can relay the block to the next host, so that in parallel you are writing it to 2 hosts. But this is just an approach that HDFS seems to be doing. You can always write one block, say you are writing block 0 on host 1. When you're done, you can go and write on host 2. It's up to you. So this is how a write will look like. Now let's try to see it in action. We said that we have made a cute little distributed file system. Let me introduce you PyDFS. These are the 3 components that will be dividing it into. We have a metadata storage. Let's call it a master. We got data hosts. Let's call them minions. And of course, we'll have clients to interact with these 2. Now, how will the file that we've been talking about /et/password will look like in this case? This is the file. We'll have a dictionary of file to block mapping. That is, a file is divided into what are all blocks. That in this case, block 0, block 1. We'll be having additional dictionaries that will track the blocks allocation, that where each block is located at. So that will be a block to list mapping. And in the end, we'll have a list of minions, that what all are our data hosts. There will be some more properties. The first being replication factor. So far in the examples, we've been creating 2 copies of each blocks. But this really is configurable. Say we discussed, like in the LinkedIn's members data set case, we want to increase the replication factor. It makes sense. So that will be one of the property, that how many copies of the blocks to create. Other will be block size. So we had a block in our typical file system as well. You have blocks in here as well. But what really different here is, in case of typical file system, the block size are usually half a kilobyte to 4 kilobytes. So this is the block size that is used in our normal file system. But in this case, because you have a really huge storage space and huge data sets, you generally increase the block size to 64 MB or 128 megabytes. So that will be a block size. And of course the block placement strategy. So metadata node does the allocation. In this case, master will be doing allocation, that where each block should be placed. In this implementation, or tiny implementation, it will be random, but in real world, you will be using some heuristic or logic to decide the block placement, like where all the blocks should be going, on what data host your block should be going. You want to use some logic after that. Let's take a look at the API. How will it look like? Master will have two functions, reads and writes. Read, you just give a file, and what it returns? Fantastic blocks, and where to find them. That is list of blocks and where are they located. In case of write, along with the file, it will take size. Why size? Because what master does is, given a file, it will divide it into blocks, and those blocks has to be placed somewhere. So to divide it into blocks, it needs size. So you give a size as well. It will do the allocation using whatever logic it uses. In this case, it happens to be random, and response would be somewhat similar. How will the minions API will look like? Well, minions will be relatively simple. Or what after all they deal with is blocks. So given a block, if you say get me this block, it can just read block from its local storage and get it back to you. If you tell it to put, it will put the block on your local disk, and it can also forward it to the other minions that like we just saw in the diagram. So if you call it put on a minion, it will write the block on the local disk, and it will call put on the next set of minions that are in pipeline. Now, how will they communicate? So obvious choice would, like the natural choice that would come first to your mind will be an HTTP API, like clients, minions, masters will be communicating over HTTP protocol. In this case, we'll be using RPC, remote procedure calls. Why? No particular reasons, but the HDFS seems to be using RPC, because after some point of time, it makes sense to use custom procedure calls protocols. So that is why we have chosen to use RPC here. We'll be using a module called RPC. Let's also take a look at some code so that it makes sense. It is there on the GitHub repo. The code is really simple. It should be approx 200 lines, so you can go home and check it out. My username is Sanket Plus. Repo is called PyDFS, and code should be under srecon branch. Let's take a look at minion first. This should be relatively simple. So this is where you start the RPC server so that you can remotely call the objects of, say, if the client, if it is a minion, then it can call other minions put. So here we just start the server. This is the class minion. So you have put will take block ID, it will take data, and it will take list of minions. What it will first do is it will write it on a local disk, whatever the block you've given, and it will call forward. What forward will do, it will connect to the remote minion. So this is the RPC calls, and it will just call put on that minion. If you want to get a block, you just give a block ID. It will read from the file and return it to you. That's simple. If we quickly take a look at master's code, these are the data structures that we talked about: file to block mapping, block to minion mapping, and of course the list of minions. You got a read, you just give it a file, it will return you the mapping, blocks to where to find the mapping. If you call a write, it will allocate blocks, and it will return the allocation. Client will be communicating with these two as we saw in the diagrams. So if you call a get, it will call a read on master because it needs to get the metadata. And for each block, it will be connecting to a minion and calling a get on minions. Similarly, it will be for puts. Now let's try to see this in action. So we'll be starting up 3 minions. These are 3 actual cloud hosts. 2 are on Azure Cloud, one is on Google Cloud, just to get the feel of real distributed file systems. We'll start the minions. So the parameters that we're giving is the port that it will be listening to and a directory where the blocks will be written. This is our master. So as you can see, we have 3 minions that are really distributed across the internet. Replication factor we are setting as 2 and block size is 100, just for this example. Let's start the master as well. So we have master running on our local machine. We got minions running across the distributed server somewhere on the internet. Now let's try to put a file. So we call a client, we say put, I'll be putting my public key and we'll be calling it pub. I hope this is readable, or should I zoom in? Let me. So when I will call a put, what client will do it'll first go to the master that is running locally. Master will do some allocation, and whatever the allocations are done, it'll call put on minions that are on some remote hosts. So let's try to see. So as you can see, put block has come. It is forwarding block to some other server. Here put block has come. So randomly blocks are getting distributed across hosts because that's what our strategy was. We'll be placing blocks randomly. So our file has been written. Some blocks are on this server. It has been replicated to this server. Some are on this. So they are basically distributed. So you put a file. Your file was divided into blocks of 100 bytes, and all the blocks are put randomly on some servers on the internet. Now, if you are to read this file, we'll call get. We'll say we want to read the pop file. That's what we put the name as. So similar workflow will happen. It will go to our master that is running locally. Master will tell that these are the blocks. These are the 2 of the 3 servers where they are located, and our clients will be contacting those minions. So you see get block has come, get block has come. One more get block, and there you go. The file is read from across the distributed hosts and it's been presented to you. Now, the one of the reason we went distributed was you can tolerate node failures. So what if one of the minions went down? Let's try to see what will happen. So we stop one minion. So all those data blocks that were stored on that minion are not available because the server is down, minion is down, something happened. Because we are distributed, we made 2 copies. Your data should still be available. Let's see if it is available. We'll call get again. Now see, the queries are coming on 3rd minion and you still have your file available. So this is one of the reasons why you go distributed. Now, what if one more minion went down? Your file might go unavailable because you created 2 copies and 2 minions are down. So there are chances that your file is not available anymore. While I'm saying chances, let's see. A case can happen where say you had your blocks distributed like this manner. Host 1 went down, host 3 went down, two hosts went down, but you still got both the copies available. So this can happen, but if host 2 went down and 3 went down, you got block 1 is missing. So let's try to kill one more and see what happens. 2 minions down. Let's try to read the file. Okay, it's still available. So it was the case that we described. So we'll do the other way. We'll start this one and kill this one. Now it should go corrupt. No blocks found, possibly a corrupt file. You can see no blocks found. So this is what it will look like in actual distributed environment. This is how the reads and writes will go. Now, where can you go from here? So this is just a toy file system. You cannot, of course, use it. It's not production usable or anything. Just to understand the concept, we used it. But these are some of the existing file system that the world uses. The most widely used or the most famous one being SDFS. That is Hadoop's database, Hadoop's distributed file system. There's also HopsFS that was created at Spotify. That's a bit of modification on SDFS. We'll see what do they do differently. And there's also Perkeep. What Perkeep does is it's a storage for your personal data. It can be replicated across storage providers like Google Drive, S3, Azure Cloud Storage. So these are some of the distributed file systems that are out there that you can check out. Now, not everything science is gold. So in this case, it sounds all good and all well, but things can go wrong here as well. What can go wrong? We initially said that what if we had only one copy of metadata? So what if metadata host goes down? So let's see how does these file system handle, because we've mentioned them. So in SDFS, in really normal basic operations, your metadata is stored on a disk, local disk. So because it's a disk, it's a single point of failure, we talked about it. So what it can additionally do is, while writing it to a local disk, it can write it to a network disk. So there you go, you got two copies. You still have one master process of the metadata node that is to solve this, but you got two copies, so you have redundancy available. Now, to make things a bit better, to get high availability, what later version of SDFS did is, you got two metadata nodes that are in active-passive mode. And the metadata actual will be written on quorum of nodes that are called journal nodes. So your metadata is always written on this journal node, say 3 node, and you got active standby configuration for metadata node. So that is how you do the HA part. What HopsFS did differently is, you get out of the journal node, instead you put a MySQL cluster. So in MySQL cluster, your data is replicated, so that thing is taken care of. And now you can have multiple metadata nodes that are name nodes in SDFS nomenclature, and they can serve your metadata requests. What Perkeep does differently here is, you don't have a concept of metadata or the metadata node. Where do you put your metadata? Well, you put it along with your data blocks. So you on the data nodes, say in this case minions, you'll be putting data as well as metadata. How do you differentiate them? Well, if you read a block and if it conforms to some specific JSON schema, it is your metadata. So that is how you read all the blocks. If the blocks conform to a specific JSON schema, it's your metadata block. You read all these metadata block and you can create a file system index, and that you put on metadata node. So you read all these blocks, and if they are found to be metadata blocks, then you know it is metadata, and you'll be putting it on metadata host. So you create an index. So if something happens to metadata node, if it gets wiped out, you can always go read all these blocks, figure out what are the metadata blocks were, and recreate the index. So that is how Perkeep does it. If data host goes down, in this case the minion, well, because you got multiple copies, they can come back up and join the cluster again, and you got your replication factor maintained. If some cases happen that this goes down or crashes and data is not recoverable, file systems also handles that by adding some complications. So we'll not go there. If you're interested, we can talk about it later. Now, these are some problems. There are some limitations, of course. So nothing. This is not one solution for all your problems. So these are some of the latent problems. The first being latency. Why? What we did? How did we make it distributed? Well, we took bunch of hosts, put it on a network. So what we introduced here is network, and with network come uncertainty, latency, things like that. So now when you read a single file, you go to metadata host first, you go to data host first, you jump networks. So of course there will be latency. So we saw in this example as well, right? So if you read a file, see how long it's taking. It's taking in seconds, like, because this is distributed across cloud. But even if you put all these in same data center, it won't be as fast as your local disk. So latency will be there because they are distributed across network. There will be operational complexity as well, because earlier it was a single disk. Maybe a driver will be there that is there to access. Now you put it on different hosts. Now your file system is distributed across hosts. So you got configuration management to do. You need to make sure that they are all version compatible. You need to maintain their uptime. So it will get operationally complex. You need some special people or team setup to maintain this. If you want to look at the components, you see this diagram on this side of the dashed line is the SDFS. So you see there are data nodes. There is a name node, active name node, standby name node. To maintain the active passive standby, you also need to operate a zookeeper cluster. You also need journal node. So tons of components that you need to manage. So this gets operationally complex. In case of HopsFS, you can see there's a, instead of journal nodes, there's a MySQL cluster, and you have n number of metadata node. So it gets operationally complex. It also doesn't work well with small files. So in the demo we saw it was a really small file, but if you are to put it on a distributed file system, it may not be optimal, because to read a really small file, you need to go to 2-3 hosts, you go over a network, and then finally get a small file. Also, you'll be using a lot more metadata space, because you got limited metadata space, because you got only one host or n number of hosts, less than data hosts. So they'll be consuming memory. So you may not want to put a lot of small file. It doesn't work well with small files. And last, but it's not an exhaustive list, uses patterns. So we talked an example of LinkedIn's data set. We'll be reading file. 10 people are reading file in parallel. So in those kind of cases, this thing scales well. You can create, instead of 10, you can create 20 copies, and reads will scale as well. But if you wanted to write to this file, 10 people are simultaneously writing it to this file, then all these distributed systems concept would kick in. You want to maintain consistency, and things will start to get more complex. So it does not really do well with the random writes cases. So that is why SDFS also restricts you to either append or read. You cannot write at any random place in the file. So these are some of the limitations, and these were distributed file system. I hope you learned something new today, and that is all from my side. Thank you. This is my home. If you want to look me up, tweet me, any feedbacks, whatever. Questions, please, if you got any.
So my query is, let us say that I'm writing and reading the file at the same time. So what exactly happens if I'm trying to do? Let us say that I'm trying to write a large file in one of the client, and another client is reading the same file. So how exactly my behavior will be?
Writing and reading at the same time. So metadata, so that's what, if you go back to this diagram, so it can happen that file is being written, and it also can happen that you wrote it on host 1 first, and host 2 was down, so it was not written. It can happen, right? You are creating multiple replicas. So what this was simple implementation, but in real case, metadata node will be keep tracking of these blocks. So if block 1 is written on host 1, host 1 will be sending some reports to metadata node. So it will tell that I have block 0 on my local disk. Host 2 will be telling I got these 2 blocks. So this is how metadata node will be knowing that these are the blocks that are supposed to go, that this file is being written, these 2 blocks are supposed to go, and in the reports it has got only 1 block, so it will know that this file has not been written yet. So metadata node can contain, can kind of maintain the state that where exactly is the process, how are the blocks, how many blocks are there, how many are missing. And in case if it goes missing, say this host went down and it never came up, so in the reports metadata node will come to know that only one copy of these blocks is getting reported. So it's kind of under-replicated.
So I mean, like,
You're following?
yes, yes. So finally, like I mean, like if the client, let us say that in that case, let us say that 3 blocks has been written. Let us say that okay, the file is not so big, 3 blocks. So let us say that first block has been completed. So let us say there is another client has been asking for the same file at that time. So will it be showing the first block content, or it will not be showing like error?
So it will depend on what file system implementation you're talking about.
I mean, in general, I'm not.
It's not in general. So
okay.
if you have to implement a file system, you can enforce that once file has been written, then only you can read. So you can implement it that way, that once it has been written, all the blocks are reported, they are confirmed to be written, then only read operation can be allowed. That can be done. It depends file system to file system. That's what I'm saying.
Thank you.
It might be a long question. Can you just give a brief idea like how the access control or security is maintained in distributed file system?
Yes, so that is also implemented at the metadata host. So because you are in this diagrams, we are simplifying things a bit, and we just have file to block mapping. But along with that, you can also have user sort of information that you have in normal file system, that who is the user, the group. So those sort of concepts can be introduced here. So this is the place where you put your access control and those kind of things, ownership.
And one more thing, like in your diagram, like you showed that clients have direct access to all the hosts, right?
Yeah.
Yeah. So is it like pretty common, like way to do it, or like mostly like there are like some kind of proxy server?
No,
like,
they,
which have
as far
all
as I
the
know,
access?
they go directly, the clients will go directly to the data hosts. So authentication methods are there, that Kerberos or those kind of things can be used. But if you start up a cluster and do a real basic setup, you will be going directly. There won't be any proxy. Because that's the point, right? Because if you say 100 clients and different files are being written, right, you should be able to go and do parallelly.
So each host will have some kind of access control, like some authentication. So
They are open. Authentication as in, so they should be accessible to clients, right?
so if you wanna implement like security, like only some users can access some files in some host. So
Yeah.
so the authentication server is like centralized, or it will be on.
So
each host?
I haven't. So the cluster I work with was on a real small number of services for using. So we didn't really implement the Kerberos or the authentication sort of methods, but they sure are available. I'm not sure how will it work centrally, but the options are there.
Thank you.